Hello, today we talk about detection of cosmic rays. One is direct cosmic ray detection, which is for cosmic rays of energy above the knee, so above 10 to the 15 electron volts, which is 1000 tera electron volts or 1 peta electron volt. And these are space-based, so we do them in space with satellites or at the edge of the atmosphere with balloons. And so this is a detection of the primary cosmic ray before it hits the atmosphere, initiating the particle shower. Instead, for energies above the knee, we use indirect detection. This is for energies above 10 to the 15 electron volts, because the flux here is, as we have seen in the last video, less than 1 particle per square meter per year. So this means that with a space-based detector, which are of the order of the square meter of aperture, we would detect only 1 or few particles per year of this type. So in order to have more data, we need to use ground-based detectors. So we detect not the primary cosmic ray, but we detect the secondary particles from the EAS, the extensive air shower initiated by the cosmic ray. To study cosmic rays in the atmosphere, it is useful to know something about the structure of the atmosphere. So here we have the height in kilometers, and here the temperature in degrees Celsius. The atmosphere can be divided into layers, and 2 layers are separated by a line. The layers end with sphere, and the line ends with pores. So the first layer is the troposphere. This line is the tropopause, which separates it from the stratosphere. Then we have the stratopause, and this layer is the mesosphere, mesopause, thermosphere, thermopause, exosphere. The troposphere goes from ground level to about 10 kilometers. Now, the height at which we pass from one layer to the other, actually this height depend on weather, they depend on latitude, so these numbers here are just very indicative. We can say that the troposphere is from 0 kilometer to about 10 kilometers, and it contains from 75% to 80% of all the air in the atmosphere. So because of gravity, the atmosphere is very dense at the ground, and it becomes a very low density as you go up. Every mountain is inside the troposphere. Keep in mind that the highest mountain in the world, the Mount Everest, is almost 9 kilometers high. And in the troposphere, the temperature at the ground level is on average 15 degrees Celsius. And as you go up, the temperature decreases almost steadily up to minus 56% because of the drop in pressure. Then we have the stratosphere. The stratosphere contains about 20 to 25% of all the air in the atmosphere. So the troposphere and the stratosphere together have basically all the air in the atmosphere. The other layers have very little air. And in the stratosphere, at the lower stratosphere, is where most commercial airplanes fly, and military planes can reach higher altitudes in the stratosphere. In the stratosphere, we begin at minus 56 degrees Celsius. At the beginning, the temperature is constant. Then we have an increase in temperature due to the ozone layer, for which the air absorbs ultraviolet light from the sun, and this increase in temperature is up to 50 kilometers, so up to the stratopause, and it reaches 0 degrees Celsius. Then the mesosphere is where most meteors disintegrate. It contains less than 1% of the total air in the atmosphere, and it goes from 50 to 80 kilometers. And here the temperature drops again. First it is constant at degrees Celsius for a little while, then it drops up to minus 90 degrees Celsius. So the mesosphere, the top of the mesosphere is it reaches the lowest temperatures on Earth. And all this drop in temperature is because the density of air, which was at the stratopause less than 1% of the total air in the atmosphere, here reaches less than 0.001%. So the thermosphere begins. At the thermosphere we begin to have the first satellites, like the International Space Station, and the temperature here increases, but first of all, this layer is very high compared to the others. It goes from 80 kilometers to 650 kilometers, and the temperature here increases because the air molecules are directly heated up by the sun, and it increases from minus 90 degrees Celsius to 1500 degrees Celsius. So why don't satellites burn up? Well, they don't burn because we have very little air. So even though the individual air molecules have a lot of kinetic energy, which corresponds to a very high temperature, there are very little air particles hitting satellites. So even if the temperature is very high, it is not hot here. It is actually very cold. Then we have the exosphere, where most satellites are, and it goes from 650 kilometers to about 10,000 kilometers. So it is a very high layer of the atmosphere with almost no molecule inside it. In fact, it is often considered not part of the atmosphere but already space. And in fact, there is not even a concept of thermodynamical quantities. You see that while in these layers the drop in temperature is due to a drop in pressure, but we don't even have enough air to define pressure and to have a drop in temperature because of the drop in pressure. It just stays constant from 1500 degrees Celsius, from 650 kilometers up to 10,000 kilometers. So cosmic ray enters in the atmosphere, which is almost empty at the beginning, so there is not much probability of interaction, and only at a certain point that we will see it will interact with the atmosphere. Now, to quantify how much material the cosmic ray has encountered, so how much it travels effectively through the material, we do not use simply the height, because as you can see in 5,000 kilometers it basically has passed through no material basically. Instead, in only 10 kilometers it passes through 70% of the whole atmosphere. So the height is not a good parameter to use to measure the quantity of material it passes through. We measure the mass above the column of air at which the cosmic ray is. So if it is here, the quantity of material it has passed through is the mass per unit area from this point to the infinite, and this is called atmospheric depth, vertical atmospheric depth, xv, which is the integral from h0 to infinity of the density in the h. So this integral gives the amount of mass per unit area above a particular height h0 of the atmosphere. So how does the density of air rho change with height h? We have two things which determine it. One is gravity and one is the ideal gas properties. So first let's start with gravity. Because of gravity, at any point of the atmosphere there is some mass of air which exerts a force equal to g times the mass of air above, and the mass of air above is rho times the volume of the air above, which is A times the height of the volume of air. So as you go up So this is the force, and as you go up, these changes are dF, and the quantity by which it changes is g rho a dz, and dz is equal to minus dh, minus the increase of height, because as you increase height, the height of the column above goes down. So this is, because of the definition of pressure, equal to A times P. So dF is equals to A times dP. So this equals this, and we obtain dP in dH equals minus rho g. Then we can treat air as an ideal gas. So we have a particular relation between the thermodynamical variables. So we have P times V equals the number of molecules times Kb, Boltzmann constant, times the temperature. So P is N, the density, the number density, Kb times T, which is the mass density divided by the mass of one molecule of air, times Kb times T. So we have dP becomes kBT divided by m g rho in dH equals minus rho g. So we have d rho in dH equals minus gm divided by kBT rho. So this differential equation is not trivial to solve, because the temperature T, as we have seen, changes with height in not a very simple way. So what we do is we change atmosphere. Instead of using the actual atmosphere, we integrate in another atmosphere. So we do the integral from h0 tilde to the infinite of rho tilde h tilde in dH tilde, and so we have a bijection from the real h, the real height, to h tilde, the height of the new atmosphere. Now the atmosphere we want is an isothermal atmosphere, so that there is no dependency on of the temperature with h, and we can solve this equation. So in the new atmosphere we have this relation d rho tilde in dH tilde equals minus gm divided by kb T0 rho tilde of h tilde. So the new profile of the atmosphere depends on what temperature T0 we choose. So we have changed map from h and rho to h tilde and rho tilde, and h tilde 0 we can write it more clearly as h tilde of h0. So we have changed map in such a way that the depth as a at h is equal to the depth at h tilde of h, with T0 equals T of h tilde equals constant. So the new atmosphere has an isothermal profile whose scale depends on the temperature chosen, T0. So we call this the inverse of this, kb T0 divided by gm, which has units of length. We call it scale height of the particular isothermic profile. So now the equation is very simple to solve. The solution is an exponential Rho 0 is the temperature, the density at h tilde equals 0 times the exponential of minus h tilde divided by the scale height. We can also write the vertical atmospheric depth in exponential form by doing the integral. So xv of h0 is the integral of this in the h, so it is rho 0 tilde times minus h0 times e to the minus h tilde on h0 from h tilde equal to h tilde 0 to infinite. And so this is to the infinite, this is 0, so we have minus minus, so plus rho 0 tilde h0 times the exponential of minus h0 divided by the scale height. So we see also that rho 0 tilde h0 is the vertical depth at h0 tilde equals 0, and this is simply the vertical depth of at 1 atmosphere, so we call it xv atm. And since we want to conserve the volume of area in the new map, we want it to represent effectively the atmosphere of the amount of air of the real atmosphere. So basically we are simply saying that 0, the height 0 get sent to the height 0, so the ground level gets sent to the ground level. So in every isothermal atmosphere, the meaning of the length scale is the same. It is the height at which the density or the atmospheric depth drops of by a factor of E. So if here we have the depth at the atmospheric level after our height h0, we have xv atm divided by E. So since this represents the air above, the total amount of air inside here is 1 minus 1 divided by E times the atmosphere at sea level, which is the total atmosphere. So in this portion is contained 1 minus 1 divided by E of the total atmosphere. So this, if we had chosen a different temperature, so if we choose a higher temperature, we will have a higher length scale, but at this time this quantity of air is contained here, so we simply have scaled to a higher atmosphere, but the meaning remains the same. So if we measure in units of length scale, we can communicate easily between different isothermal models. This is the graph of the vertical atmospheric depth in function of the height in an isothermal profile. As you can see, it is a decaying exponential, and since we are measuring the height in units of scale height, this graph is the same for every isothermal profile independently on the choice of temperature. We are measuring the x-axis in units of 1 atmosphere. 1 atmosphere is the atmospheric depth at ground level. So at ground level we have 1 atmosphere, and at height 1 scale height we have e to the minus 1 atmospheres. 1 atmosphere is 1000 grams per square centimeter. How much is that? Let's compare it with water. How high should a column of water be to give the same pressure? We have that the density of water is 1 gram per cubic centimeter. So a volume of water with a height such that it gives this atmospheric depth must be height 1000 centimeters, which is 10 meters. So 1 atmosphere corresponds to 10 meters of water. Now let's calculate the scale height for a particular temperature. So first let's calculate the ratio between the scale height and the temperature. So Boltzmann constant is 1.38 times 10 to the minus 23. G is 9.81, and the mass of one molecule of air is, air is composed of diatomic oxygen and diatomic nitrogen, 80% of nitrogen, 20% of oxygen. So the mass of one air molecule is the mass of a nucleon, which is the mass of a proton, which is about the mass of a neutron, times the number of nucleons in the molecules. We have 4/5 of nitrogen, which has atomic number 7. So 7 times 2 is the number of nucleons in one atom. So in one molecule it is 7 times 4, plus 1/5 oxygen, which has in one molecule 8 times 4 nucleons. So this is 4 divided by 5 mp times 16 divided by 5 mp times 7 plus 2, so times 9. So 16 times 9 divided by 5 times the mass of the proton. So the mass of an air molecule is 16 times 9 divided by 5 times 938 mega electron volts. 1 electron volt is 1.6 times 10 to the minus 19 joules, and divided by c squared, so times 9 times 10 to the minus 16. So we are in SI units, so that when we plug it here in SI units, the mass of an air molecule in SI units, we get the result in meter per Kelvin. So H0 divided by T0 equals 138 divided by 981 times 5 divided by 16 times 938 times 1.6. So let's write here 16 and here minus 20, so times 16, and then we have the powers of 10 to the minus 23 minus 6 plus 20 plus 16 meter per Kelvin. So this is about 2.93 times 10 to the minus 6. I did this with the calculator. Then we have these powers of 10, so minus 29 plus 36, so minus 29 plus 30, so times 10 meter per Kelvin. So this is about 29.3 meter per Kelvin. So we obtained the scale height temperature ratio, which is universal across every isothermal profile of the Earth's atmosphere. Now if you change planet, you change composition of the air, so you change the mass of the air molecules and you change the gravity. So you can use this formula also for other planets, but you must plug in the respective values for the molecules of air, for the mass of the molecules of air, and for gravity. On Earth it is about 29.3 meters per Kelvin, and you can now obtain the scale height for a particular value of the temperature. For instance, if you choose the average temperature of the ground, which is 15 degrees Celsius, this is corresponds to 288.15 Kelvin. Then you multiply this by that and you get the scale height. You would get about 8.4 kilometers. So remember the meaning of the scale height. It is the height at which we have e to the -1 of the entire atmosphere above and 1 minus e to the -1 of the entire atmosphere below. In this atmospheric profile, this happens at 8.4 kilometers. In the real atmosphere, this happens at about 7.5 kilometers. So, in this isothermal profile, this height of 7.5 kilometer gets mapped to 8.4 kilometers. At what atmospheric depth cosmic rays interact depends on the interaction cross-section. The interaction cross-section of a beam of particles of section A hitting a target particle is defined as the product between the probability of interaction of the beam with the particle times the area A, so that the probability is interaction cross-section divided by the area of the beam, so that the interaction cross-section is like an effective target area. If this beam travels a distance dx of air, and in this volume of air, A times dx, there are dn particles, then the probability of interaction is sigma times dn divided by A, which is sigma times n divided by the volume A dx. So the probability of interaction is sigma n dx, where n is the number density of the target. The number of particles left in the beam are the particles which have not yet interacted. So dnb, the difference of the number of particles, decreases by an amount proportional to the number of particles in the beam times the probability of interaction, which is sigma nt dx. So this is the decrease of particles of the beam after traveling a distance dx. The solution for a medium with constant density would be an exponential, a decreasing exponential. Nb equals n0, the number of initial particles, times e to the minus x to the minus n target sigma times x. N target sigma 1 divided by n target sigma is defined as the interaction length. So this is usually written as nb equals n0 e to the minus x divided by lambda. So one interaction length is similar to the scale height. It is the length after which the initial number of particles in the beam drops of a factor of e. But the particle density of air in the atmosphere is not constant at all, so we do not use the length but the atmospheric depth. So we multiply this by rho. So we have d rho x, which is the differential dxv, the differential of the atmospheric depth, So the differential of the number of particles in the beam now is minus mb sigma, and now we must divide by rho. So number particle number density of the target divided by rho, the density, the mass density of the target. So this is nv, n target v divided by n target mv, where m is the mass of one m molecule. So this is 1 divided by m. And so we now have nb equals n0 times minus sigma divided by mx. So we now have the interaction length in units of atmospheric depth. So it is called lambda I, to distinguish it with lambda's interaction length, and it is defined as n divided by sigma, so that we can write this as nb equals n0 e to the power of x divided by lambda I. And lambda I does not depend on the density, because we have already included the density in the variable x, this xv. At what atmospheric depth do cosmic rays interact on average? The average distance traveled in atmospheric depth is the integral from 0 to infinity of the number of cosmic rays interacting in a particular interval dx times the distance xv. It would be at that particular interval, so xv times the number of cosmic rays interacting here is minus dnb, minus because dnb is negative because they decrease. Why is that? The number of cosmic rays is a positive quantity, and this divided by the total number of cosmic rays. So this is, we can change variable of integration. In fact, from 0 to infinity is from depth 0 to depth infinity, and this is this integral can be done by parts. So let's write 1 divided by n0 times this integral by parts is the derivative, so we have minus nb times xv from 0 to infinity minus the integral from 0 to infinity of minus nb, so plus nb times the derivative of this, which is 1, in dxv. So this is 1 divided by n0 times where this is at the infinite, it is 0 because it is an exponential of minus infinite, and at 0 it is 0 because it is multiplied by 0. So we are left only with that integral there, which is n0 times the integral from 0 to infinity of this exponential minus xv as by lambda in dxv. So it is minus lambda I times the exponential of minus xv divided by lambda I from 0 to infinite. To infinite it becomes 0, so it is minus lambda I times this to the 0, so lambda I. So the average atmospheric depth is lambda I, the interaction length. Interaction cross-section depends on the cosmic ray, it depends on the energy of the cosmic ray, and they can be found in laboratory. The typical value for protons in cosmic rays are about, for instance, 80 grams per square centimeter, which is a fraction. Remember that the atmosphere is 1000 grams per square centimeter, so it is a fraction 8% of the atmosphere. So when cosmic rays, when these protons typically interact, they have already passed 80% of the atmosphere. This corresponds to, if you recall, the profile of the atmosphere we had drawn at the beginning. It corresponds to the higher stratosphere. And let's calculate the scale, the unit of scale height, how much this is. So remember that the scale height, at k scale height, we have above e to the minus k times the atmospheric depth at the ground. So when is e to the minus k times the atmospheric depth at the ground equals to 80 gram per cubic per square centimeter, which is that e to the minus k equals 80 divided by 1000, so 8 divided by 100, so k is the logarithm of 100 divided by 8, and this corresponds roughly to 2.5. So this lambda I corresponds to 2.5 scale heights, depending on whether this corresponds roughly to 20 to 22 kilometers above the ground, which is the middle stratosphere, and this gives us an idea of how high we must go with balloons if we want to catch primary cosmic rays before they interact with the atmosphere. But this value of height is only if you want to catch cosmic rays coming straight from above, perpendicularly to the ground. So this is the Earth, and this is the value if for cosmic rays which go straight to the Earth. This is the atmosphere, but many cosmic rays hit the atmosphere at every direction. So if you want to, if your device measures the cosmic rays coming from any direction, then you must go higher up. You must go at 27 kilometers. So this interaction length this time is not the length of vertical atmospheric depth, but a length of slant atmospheric depth. As you can see, when they do not travel straight from perpendicularly to the ground, they have more atmosphere to travel to reach the same height. Now, if this angle is less than 60 degrees, typically you can approximate the Earth to a flat Earth. This is very useful because in this way it is very easy to relate the slant depth to the vertical depth, because in a flat Earth every layer of the atmosphere, the differential, if you take the differential xv in a layer of the atmosphere, the corresponding differential of slant depth has this relation. The vertical differential is the slant differential times the cosine of the angle theta, and this is, in a flat Earth approximation, true for every layer of the atmosphere. So this is true for the total slant depth. The total vertical depth is the slant depth times cosine of theta. So the total slant depth is xv divided by cosine of theta. And if theta is at the limit 60 degrees, then the cosine of theta is 1/2. So the slant atmospheric depth is the double of the vertical atmospheric depth. And if we take the total atmosphere, then the total atmosphere, we know the vertical atmosphere is 1000 grams per square centimeter. Then the slant atmosphere at 60 degrees is 2000 grams per square centimeter. So this slant atmosphere contains twice the air of this vertical atmosphere, but at this point this formula starts to be not very accurate. In fact, if we kept using this formula, if we kept using the flat earth approximation, we would get that the slant depth is infinite, because if the earth is flat, then it continues like this to the infinity, and then a horizontal ray would have to traverse an infinite atmosphere. The flat earth approximation would overestimate the slant depth. In fact, we have now this differential formula for every differential layer, and as you can see, in the flat earth approximation, all layers 1, 2, 3, 4 look the same. The vertical depth, which is in black, is always at the same angle to the slant depth, which is in red. And so we can integrate, leaving out cosine of theta, and we get the formula that we got before. Instead, in the round earth, as you can see, because of curvature, now the angle narrows down as you go in upper layers, and you must take this into account when taking the integral. In particular, the horizontal atmosphere is significantly thicker than the vertical atmosphere, because the air passes a lot through the densest layers. In fact, the horizontal vertical depth, xh, is equal to 36,000 grams per centimeter square. Compare it with the vertical depth of 1000 grams per centimeter square. So it is the horizontal atmosphere is 36 times thicker than the vertical atmosphere. If you take into account every direction, the average height at which protons hit the atmosphere goes up from 22 kilometers of only vertical protons to 27 kilometers for protons coming from any direction. So if you want to catch most of primary protons, you must go higher than 27 kilometers. For direct detection of primary cosmic rays from satellites or from balloons, we use typically a time-of-flight device, a magnetic spectrometer, and a calorimeter. The time-of-flight device can measure the velocity of the incoming particle, as well as the energy loss, which is proportional to minus z square for heavy relativistic particles, so protons and nuclei, which is the Bethe-Bloch formula. The Bethe-Bloch formula, which is the formula for ionization excitation, which is the dominant process for these particles. But for high energy, this system fails because we cannot measure anymore the velocity, because for high energies the velocity is more and more indistinguishable to the speed of light. Then we have the magnetic spectrometer. The magnetic spectrometer we have seen in the last video. It measures the rigidity, momentum divided by charge, and it can measure the charge sign. This also fails at higher energies, because at very high energies the path through the spectrometer is basically a straight line, because it is very difficult to bend a high energy particle with a magnet. Then we have the calorimeter. The calorimeter can measure the energy by counting the number of particles in the secondary shower produced by the cosmic rays, because the calorimeter is a thick layer of material. When the primary cosmic ray hits it, it produces a shower of particles, which according to Heitler formula can give you the energy by counting the number of secondary particles. And when all this energy this energy is absorbed by the calorimeter, which can be counted by counting the particles and the types of particles in the shower. The secondary particles can tell you the type of primary particle which hit the calorimeter. We have some constraints that we have seen for high energetic particles. The time of flight device starts to fill pretty early, followed by the magnetic spectrometer, but other constraints come from practical constraints when carrying objects on balloons or in space, because we cannot carry heavy devices. So our device is pretty limited, and we must often choose what to focus on. So often we will not have the three together, but sometimes we will use only a magnetic spectrometer and not a calorimeter. Sometimes we will renounce to the magnetic spectrometer and we will focus on the calorimeter. It depends on what we want to focus on. An example of direct cosmic ray detector is BESS, the balloon-borne experiment with a superconductivity spectrometer. It was a balloon flying above Antarctica, because Antarctica is in the South Pole, and so there are a lot of low energy cosmic rays, and also because the vortices in the South Pole could keep the balloon afloat. And it is a Japan-USA collaboration. It has been operating from 1993 to 2008. The energy range of the detected particles were from 0.1 gigaelectron volt to 160 gigaelectron volt, so it is in the low energy range, and it had a time of flight device made of layers of plastic scintillation counters, one at the top and one set of layers at the bottom, which could measure the velocity and the charge through the ionization excitation Bethe-Bloch formula. And it could also discard particles which were coming from below from those coming from above, because those coming from below would be due to particles bouncing after hitting the atmosphere, and so it wouldn't give clean data. Then there is as magnetic spectrometer a superconductivity solenoidal magnet of about 1 Tesla in a jet drift chamber, which could give you the rigidity, and it has no calorimeter. Calorimeters are heavy, and they decided to focus everything on these two devices. And there is, by the way, an Aero-Churylenko chamber, because at high energies, the time of flight device cannot measure the velocity, so you cannot distinguish between electrons and antiprotons. BESS wanted to measure antiprotons, but antiprotons are very few, so you could not measure them by simply relying on the time of flight device, which would fail at high energies. So you had only at these high energies you had only the data from the superconducting magnet, so you would have the momentum, but you could not tell whether the high momentum would be because of a high mass or because of a high velocity. So you use the Aero-Churylenko counter to see whether the particle is moving fast, so it is an electron, or whether it is moving slow, in which case it is an antiproton. This time an example of satellite detector, PAMELA, a payload for antimatter exploration and light nuclei astrophysics. It was an international collaboration with Italy, Russia, Germany and Sweden. It was launched from Kazakhstan, and it has operated from 2006 to 2016. It was a LEO, it means low Earth orbit satellite. It was orbiting in the thermosphere, and The energy range it could detect was from 50 megaelectron volt to 1.2 teraelectron volt, so up to about 10 times more than the BESS experiment. The time-of-flight device, like the BESS experiment, has layers of plastic scintillation counters, but now there is one layer at the top, then at the middle, and at the bottom above the calorimeter, because this time it has a calorimeter. The time-of-flight could, like in BESS, measure the velocity, the charge, and the square charge. So not the sign. The sign was left for the magnet, and also the particles coming from below, and it also would trigger a signal to the calorimeter to tell it when it would pass, to tell it to turn on and be ready for the measurement. And then there is, as magnetic spectrometer, a permanent magnet this time, and then as a calorimeter there is an electromagnetic calorimeter, which can distinguish leptons from hadrons, because electronic showers have a lot of photons and electrons. Instead, hadronic showers has also muons in them, and they can be distinguished with this, and it also has a neutron detector, because some showers initiated by the proton, they have some probability of creating only electromagnetic showers, because when a proton hits a nucleus, it can transfer energy to pions, positive and negative, and neutral pions. On average, the energy is 1/3 to the positive pion, 1/3 to the negative pion, and 1/3 to the neutral pion. But there are fluctuations for which almost all the energy can go to the neutral pion, in which case it will decay as gamma rays, and then you have only an electromagnetic shower. So you cannot with a calorimeter distinguish from these rare proton showers. You cannot distinguish these from the positron showers, since positrons are rare also. You cannot tell whether this was a rare proton shower or a rare positron, and so you use a neutron detector, because when the proton interacts, it also shatters the nucleus, releasing neutrons. So if there are neutrons, it was a proton. If there are no neutrons, it was a positron. Thanks to this ability to accurately distinguish between positrons and protons, Pamela could detect the positron anomaly, which is an excess of positrons. There are more positrons than expected in space. There are various hypotheses for this, like maybe there is some nearby source, like a pulsar, or maybe there is annihilation and decay of dark matter into electron-positron pairs, and another hypothesis is evaporation of primordial black holes. Another satellite experiment is DUMB, the Dark Matter Particle Explorer, which was nicknamed Wukong after the Monkey King. It is led by China in collaboration with Italy and Switzerland, and it was launched in 2015, and it is still operating. It is a low Earth orbiting satellite in an SSO orbit, which is a sun-synchronous orbit, and the energy ranges it can detect go from 5 gigaelectron volt to 100 teraelectron volt, so 100 times more energetic than the particles detectable by Pamela. It has no time-of-flight device, and it has no magnetic spectrometer. Instead, it is all focused on a very deep calorimeter. It is the deepest calorimeter sent in space. It has a vertical depth of 256 grams per square centimeter, which corresponds to 32 radiation length of 8 grams per square centimeter. Now the radiation length is like the interaction length, but for the energy loss in the electrons due to Bremsstrahlung. So it means that if the electron was very energetic, it would lose e to the minus 32 times its initial energy. Actually, it is stopped by the calorimeter because it reaches the critical energy much sooner than reaching e to the minus 32 energy. When it reaches the critical energy, Bremsstrahlung stop and ionization and excitation energy losses dominate, and so it can absorb a lot of energy, this calorimeter, and it can also it does not need a time of flight because it can also tell the direction from which the ray came. The only thing that it cannot distinguish matter from antimatter because it does not have a magnetic spectrometer, so it can tell the absolute charge, but it cannot tell the sign of the charge. The next detectors I want to talk about were mounted on the International Space Station, so let me introduce you to ISS. The first part was launched in 1998 and it was built in orbit. It is about 100 meters in length. It also orbits the thermosphere in a 93 minutes orbit, and it can also be seen with the naked eye at the right time with the right conditions, and at the same time there are 7 members on board and each one of them gets changed after about 6 months. The station will be operating until 2030 or 2031 when it will be deorbited and destroyed in the atmosphere. Another important detector for primary cosmic rays is AMS-02 on the International Space Station, the Alpha Magnetic Spectrometer. This is the largest particle physics detector in space. It was launched in 2011 on the International Space Station by NASA, and it can detect energies between 0.1 GeV to 2 TeV. It is considered to be the spiritual successor of Pamela. Like Pamela, it is a hybrid detector, which means it has a time-of-flight device and both a magnetic spectrometer and a calorimeter, but it is overall larger. Unlike Pamela, it is on the International Space Station, so it does not have the same constraints because it was not launched at once, but it can be constantly upgraded. The magnetic spectrometer actually has a weaker magnet than Pamela, but it has more silicon layers, which means high precision tracking also for high energetic particles. At the top it has a TRD, a transition radiation detector, which detects X-rays emitted by cosmic rays through the material of the detector. So it can distinguish positrons from protons because positrons emit a lot of X-rays when passing through this material, while protons emit very little of them, and this is a much faster filter than the neutron detector which was on Pamela. At the bottom it has a ring imaging Cherenkov detector which measures velocities to distinguish isotopes and also works as a further filter for protons. Before being destroyed in the atmosphere with the International Space Station in 2031, they are planning future upgrades. One is to increase the acceptance by 300%, which means that it will be able to detect 3 times more particles. This is done by increasing the angle of detection, and another upgrade is more layers for the magnetic spectrometer. This is done in order to track higher energy particles and possibly solve the debate about the origin of the positron excess, because there are more positrons than expected from simply from secondary positrons. So it means that there is probably a primary source of positrons, and the main hypotheses are a nearby pulsar or annihilation and decaying of dark matter into electron-positron pairs. Another important detector on the International Space Station is CALIT, the Calorimetric Electron Telescope. It was launched on the International Space Station in 2015 from Japan. It can detect energies between 1 GeV and 1 PeV, and like damper, it is only a calorimeter, so it cannot distinguish between matter and antimatter. Unlike magnetic spectrometers, calorimeters cannot separate the positron flux from the electron flux. They can only measure the positron plus electron flux, but they can measure it at higher energy than magnetic spectrometers. And there is some interesting debate around the 1.4 teraelectron electron volt, because Damper has measured a sharp peak in this region, which would suggest, for instance, the presence of dark matter annihilation, but only Damper has measured this peak. CALET and any other calorimeter, they have never detected this peak, so this remains a point of debate. The next upgrade on the alpha magnetic spectrometer can tell us more about the energy range between 1.4 electron volt and maybe by measuring the ratio between the positron flux and the electron plus positron flux, tell us more about the nature of this peak, because if it is due to dark matter annihilation, we expect a higher amount of positrons. Now some results of the experiments. Let's start from heavier cosmic rays, so protons and nuclei. Their composition is similar to those found in the solar system, their distribution, but there is an exception, an important exception, which is lithium, beryllium and boron. So elements 3, 4 and 5. These elements in the solar system are basically absent because they are used inside the stars to as catalyst of the nuclear fusion, so they are not released in the end, and in the solar system there are very little of them, but in cosmic rays there are a lot more of these elements. The ratio of the quantity of this element with respect to the quantity of carbon, nitrogen and oxygen in cosmic rays is 10 to the 5 times the ratio in the solar system. This is an indication that lithium, beryllium and boron in cosmic rays are galactic secondaries, so they are not emitted like this by the source, but they are formed by spallation, which is a process for which a heavy nucleon hits a proton, and this high energetic collision shatters the heavy nucleon into smaller parts like lithium, beryllium and boron. And as a result is the energy distribution for protons and cosmic rays from energies from 10 gigaelectron volt to the near, which is 10 to the 15 electron volts. It is a power law with the exponent of minus 2.7, and we have talked about this in detail in the last video. Another observation are antiprotons detected by Bess, Pamela and AMSO2. Antiprotons are formed when a high energy cosmic ray proton hits a proton of the interstellar matter. The energy threshold for this process is 7 gigaelectron volts, and this collision creates a proton-antiproton pair. The number detected for these antiprotons perfectly match those expected by this process, though there is no evidence of any source of heavy antimatter other than this process. And for heavy antinuclei, we only have some candidate events detected by MSO2 for antihelium, but we have very little data about heavy antinuclei, so there is no evidence of any source of heavy antimatter other than cosmic rays colliding with interstellar matter. And the electron-positron flux was observed. It follows a power law like the cosmic ray flux, but it is steeper. The exponent is minus 3.1, and it has a cutoff already at 1 teraelectron volt, because electrons lose energy very quickly, so there are very few electrons which can arrive energetically to the Earth, and most of the electrons we see are from nearby sources, and instead the positron fraction of the total electron plus positron flux is larger than that one expected for only secondary positrons, while electrons, 90% of them are from our primary origin, and only 10% of them are of secondary origin, from collisions. Instead, the positrons should be all of secondary origin, but since we have observed that there is an excess of positrons, probably there is another source of primary positrons, like probably a nearby pulsar or dark matter annihilation. For higher energies we need indirect detection. We must let the Earth's atmosphere act as a calorimeter, so the cosmic ray hits the atmosphere and initiate an extensive ice shower. Detectors on Earth can measure the number and type of secondary particles from the shower. They can detect the light produced by the shower, but this can be done only at Mueller's nights, which is only about 5 to 10% of the total amount of time, and they can reconstruct the energy of the primary particle by counting the number of secondary particles and the angle of direction at which it hits the atmosphere from the time of arrival at different detectors, at distant detectors. And so if it is perpendicular, for instance, it will hit all detectors simultaneously. And the mass of the shower, the mass of the primary cosmic rays is more difficult to reconstruct, and we must analyze the secondary particles to see if it is a hadronic shower. The leptonic shower, we must see the depth to see if it is a heavy nucleus or a proton, and we have also uncertainties on high energy physics because we cannot test these energies with particle accelerators. These are two energy particles, so there are some assumptions which depend on the model used for high energy hadronic physics. When a cosmic ray proton hits a nucleus in the atmosphere, it can create particles like pions, kaons, protons, neutrons, and the neutral pions decay pretty quickly into two gamma rays, and the gamma rays into electron-positron pair, and so on, and so it initiates an electronic cascade of particles which dominates the shower, and then the positive and negative, so the charged pions, they decay into muons and a muonic neutrino, and the muon is a heavy particle which can reach the ground without interacting much, without losing much energy, and it can even reach underground detectors. So muons dominate the shower at the ground, while instead the electronic shower dominates the overall shower, especially at the shower maximum. The shower maximum is when there are most particles in the shower, and after this maximum the energy gets distributed, when the energy is distributed in particles of energy which is not high enough to continue the shower, and it is also absorbed by the atmosphere, then the number of secondary particles starts decreasing. This is how the distribution of energy into different particles might evolve in a hadronic shower. In the process, this is the total fraction of energy. In the process, the energy is lost through low energy particles in the air, so the total energy of high energy particles decreases, and these high energy particles are hadrons, electrons, and gamma rays, so the electronic component, and muons and neutrinos. Now the hadrons have the energy distributed in hadrons has an exponential decay. Then at the very beginning, the E plus minus gamma are produced, and they reach a peak of energy here, and then they slowly decay, and after a little while, because the pi plus minus take more time than the pi0 to decay, they start producing muons and neutrinos. These are the particles which dominate the fraction of energy for at the ground level. This is the atmospheric depth. This is the height of the atmosphere, the boundary of the atmosphere, and as we move to the right, we go to the ground, and there are more and more muons and neutrinos, and less hadrons. Here it is difficult to distinguish the muonic curve from the neutrino curve because they're very close together. So what we do is we expand the lower part of the energy fraction. So by taking the logarithmic scale on the y-axis, so now we have 0.1%, 1%, 10%, and 100% of total energy, so that in the hadronic component, which decays exponentially in a logarithmic scale graph, becomes a straight line, and now we can distinguish the muonic component from the neutrino component. By contrast, a gamma ray hitting the atmosphere initiates an electromagnetic cascade. This cascade is dominated by gamma annihilation and Bremsstrahlung, which are the processes which dominate at higher energies for photons and electrons. Photons get gamma annihilation if the energy is, this can only happen if the energy is greater than 1 megaelectron volt, because the mass of one electron is 0.5 electron volts, so the gamma can become 1e plus 1e minus, and at high energy, if energy greater than some particular critical energy, the E plus and E minus are subject to Bremsstrahlung, which means in German breaking radiation, which is energy losses by emitting gamma rays. So this E plus emits energy, it emits energy in form of a gamma ray, or a photon in general. So they create other gamma rays, which in turn can do the gamma annihilation again, and the electron and positron products can radiate another gamma ray, and so on. And this is the electronic cascade. In this electronic cascade, there are no hadrons as products, and there are no muons. Here this cascade begins until, so the energy is spread out in different particles, and at the end, when the energy for one particle is equal to the critical energy, which in air is 86 megaelectron volt, then this stops being the dominating process, Bremsstrahlung, and instead the dominating process becomes ionization, excitation, energy loss. So they stop the cascade, and we get to the end of the cascade. There is the radiation length here, the radiation length of 38 gram per square centimeter in air. What is the radiation length? We have talked about that, we have mentioned that in the calorimeter. It is a bit like the interaction length, you know, for cosmic rays. You have the number of cosmic rays equals n0 times an exponential of minus the length that they have traveled in the material divided by the interaction length. So the interaction length is in this context is the length after which the number of particles decrease of a factor of E. Instead, in Bremsstrahlung, we have the energy which follows a similar law. We have the energy equals E0 times the exponential minus x divided by x0. X0 is the radiation length. So in the Bremsstrahlung case, the radiation length is the energy at which the electron loses, with the electrons lose E of their energy. Sorry. So we can study Hydra's model of electromagnetic cascades. So we have that one particle creates two particles, and so on. And we have that statistically, the product, the energy is produced half of our particle and half for another particle. So we have this equipartition of energy statistically. In Hydra model we use this equipartition. So we start with energy E0, then we will have energy E0 half, then E0 4, and so on, up to E0 n, with n equals 2 to the k, where k is the number of steps. And at each step we have first one particle, then 2 squared, and so on, up to n equals 2 to the k particles. So at the denominator here we have the number of particles because it is the energy 0, if you will distribute it into 2 to the k particles. And let's say that at this step we reach the critical energy, so let's k this step k star, and we have 2 to the k star particles, and the critical energy EC will be E0 divided by 2 to the k star particles. Now, how deep in the atmosphere is that step? We must use, to calculate the length, the depth of one step, the Bremsstrahlung formula. So E equals E0 times e to the minus x divided by x0. So we have that for this to be equal to E0 half. So for one step, we have that e to the minus x divided by x0 must be equals to 1 half. So this must be equals to 2, and so x is equal to x0 times the logarithm of 2. So this is the length of one step. Now we have how many of these steps? We have k star for these steps, and so in the end the total depth will be xf plus xf is the depth at which the first the gamma ray hits the first not it hits it begins the first process of annihilation. So it is xf plus this length, which is x0 logarithm of 2, and no, sorry, times k star. And k star is, we can see it from here, 2 to the k star is 0 divided by EC, and so k star is the logarithm in base 2 of E0 divided by EC, which is the logarithm of E0 divided by EC divided by the logarithm of 2. So in the end the depth of the shower the depth of the shower maximum is xf plus logarithm of E0 divided by EC divided by the logarithm of 2 times x times the logarithm of 2. So it will be x0 times the logarithm of E0 divided by EC. In a shower initiated by a gamma ray, there are no hadrons. So this is a way in which you can distinguish a shower initiated by a gamma ray and a shower initiated by a proton or a nucleus. For instance, this is a shower initiated by a proton, which hits the nucleus of the atmosphere and it shatters the nucleus, and the products are pions, positive and negative, and the neutral pions, the positive and negative pions, the charged pions, they decay into muons and neutrinos, and these are the components which are seen mostly close to the ground. Instead, this is the pi 0 decays into 2 gamma rays very quickly, and so we have at the very beginning the electromagnetic shower, which will reach the maximum that we have seen. So if now XF is when the pions decay, then this is the formula we have seen for the maximum electromagnetic shower. But if instead of a proton we have a nucleon with number A, then we use the superposition model. The superposition model says that we can model the nucleon as the nucleus as distinct nuclei which are independent. So it is as if we had A nuclei, each one with energy E0 divided by A. So at this point, the maximum, for the maximum we must put E0 divided by A, the energy of one nucleon inside, and this gives XF plus this minus X0 logarithm of A. So the maximum the maximum for a nucleus, the maximum of the electromagnetic shower for a shower initiated by a nucleus of number A is the maximum for a shower initiated by a proton minus X0 times the logarithm of A. So while the decay products tell you whether it is a hadronic shower or a pure electromagnetic shower, so if it is initiated by a nucleus or a proton, or if it is initiated by a gamma ray, in case of a hadronic shower, the depth of the maximum can tell you whether it is initiated by a proton or by a nucleus with with mass number A. So this was an introduction to the methods which allowed us to determine the energy distribution of cosmic rays, which we have seen in the last video. See you next time.